The morning of November 7th, 1944, above the skies of Omura, Japan, Lieutenant Sadao Yamaguchi pressed his A6M0 into a climbing attack run he had executed dozens of times before. Below him, a formation of American B-29 Superfortresses droned toward their target, massive silver bombers that seemed to move with the slow confidence of whales crossing an ocean. Yamaguchi had shot down 2 B-17 seconds over the Philippines the previous year. He knew the drill: approach from below and behind, exploit the blind spot beneath the tail, rake the fuselage with 20mm cannon fire, then break away before the waist gunners could track him. But as he closed to 800 meters, something happened that would haunt his flight reports for months afterward. Every gun turret on the nearest B-29 swiveled simultaneously toward his aircraft. Not tracking, not searching, they simply rotated as one, like the eyes of some enormous mechanical predator that had sensed his presence. Before he'd even committed to the attack, the tracers came before he could process what he was seeing, a converging cone of 50 caliber fire so precise it seemed mathematically impossible. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Yamaguchi yanked his stick hard left, feeling the Zero's lightweight frame respond instantly, but 2 rounds had already punched through his port wing. He dove away, heart hammering, and watched from 4,000 meters below as 3 more Zeros from his squadron attempted their own attacks. The B-29 seconds didn't scatter. They didn't weave. They simply rotated their turrets with that same eerie coordination, and the sky filled with intersecting streams of tracers that seemed to anticipate every maneuver before it happened. 1 Zero erupted into flames. Another spiraled downward, trailing black smoke. The third broke off, just as Yamaguchi had, unable to comprehend what he was witnessing. In the debriefing that evening, Yamaguchi tried to explain it. The bombers knew where we would be, he told his squadron commander. Not where we were. Where we would be. His commander, a veteran of China and the Solomons, had no framework for understanding such a claim. American bombers were supposed to be vulnerable during the bombing run, their gunners overwhelmed by simultaneous attacks from multiple angles. That was doctrine. That was how air combat worked. But something had changed in the 18 months since the B-29 entered service, something the Japanese High Command had not anticipated and could not immediately explain. What Yamaguchi had encountered was not magic or superior American reflexes. It was mathematics, translated into mechanics, expressed as a lead computing gunsight that calculated deflection angles faster than any human brain could process. The system had a designation: the General Electric Central Fire Control, integrated with the Mark 15 computing gunsight. And before it ever proved itself over Japan, before it saved thousands of American air crews and contributed to the systematic dismantling of Japanese air defenses, it had been dismissed, mocked, and nearly abandoned by the very men whose lives it would eventually save. The story of this technology begins not in the skies over Japan, but in the bureaucratic corridors of Wright Field, Ohio, and the proving grounds of Eglin Field, Florida, where in 1942, a team of engineers faced a problem that seemed almost absurdly simple. American bomber gunners couldn't hit anything. This was not a matter of courage or training. It was physics. When a bomber traveling at 200 miles per hour encounters a fighter approaching from a perpendicular angle at 300 miles per hour, the gunner must aim not at the fighter, but at the empty space where the fighter will be by the time the bullets arrive. This calculation, called deflection shooting, requires the gunner to estimate the fighter's speed, angle of approach, distance, and rate of closure, then adjust his aim accordingly, all while sitting in a cramped turret, hands numb from cold at 25,000 feet, adrenaline flooding his system as tracer rounds streak past his position. The human brain, even a well-trained one, cannot perform these calculations with consistent accuracy under combat conditions. Army Air Force's gunnery statistics from 1942 made this brutally clear. It took an average of 3,000 rounds of 50 caliber ammunition to down a single enemy fighter. 3,000 rounds. The B-17's entire ammunition load was approximately 11,000 rounds distributed across all positions. In theoretical terms, a fully loaded flying fortress could engage roughly 3 or 4 enemy fighters before running dry, assuming perfect distribution of ammunition, no jams, and no wasted shots. In practice, gunners fired at shadows, at empty sky, at the spaces fighters had occupied a second before, their tracers drawing elegant, useless arcs through the air while the actual targets maneuvered untouched. The losses were staggering. In 1943, before the introduction of long-range fighter escorts over Europe, bomber groups regularly suffered casualty rates of 25 to 30% per mission. Entire squadrons were effectively destroyed and rebuilt every few months. The mathematics were unsustainable. At that rate of attrition, the combined bomber offensive would exhaust its crews before it could achieve strategic effect. Into this crisis stepped a technology that seemed, to the average gunner, like something from a science fiction pulp magazine. The General Electric engineering team, led by a group that included hydraulics, specialists, and analog computer designers, proposed a system that would remove the human element from deflection calculation entirely. The gunner would simply track the target in his sight. The mechanical computer, a sophisticated assembly of gyroscopes, servo motors, and analog calculating mechanisms, would measure the target's angular velocity, compute the required lead angle, and automatically adjust the gun position to the correct deflection. The gunner pulled the trigger. The machine aimed the gun. The system weighed nearly a ton per bomber. It required hydraulic lines running throughout the aircraft, electrical connections to synchronize 5 separate turret positions, and a maze of mechanical components that seemed designed to break, jam, or fail at the worst possible moment. When engineers first presented the central fire control system to veteran gunners at Eglin Field in early 1943, the reaction was not enthusiasm. It was derision. Master Sergeant Raymond Hall, a gunnery instructor with 2 years of experience training crews for the 8th Air Force, summed up the prevailing attitude in a post-war interview. "We thought it was the dumbest thing we'd ever seen. You're asking a kid from Nebraska to trust his life to a box of gears and oil. We taught them to aim, by instinct, by feel. You see the fighter, you put the ring on him, you lead him like you're shooting ducks back home. Now they're saying, forget all that, let the machine do it." Half the guys thought it was a joke. The other half thought it would get them killed. This resistance was not irrational. It reflected a reasonable skepticism born from experience. Military technology in 1943 was notoriously unreliable. Radios failed, bomb sites jammed, hydraulic systems leaked. The idea of entrusting one's survival to a complex mechanical calculator that had never been tested in actual combat seemed like madness, especially when the alternative was a manual gunsight that, while ineffective, was at least simple and familiar. A gunner could understand a ring and bead sight. He could fix it if it broke. He could aim it, even if everything else on the aircraft failed. The central fire control system, by contrast, was a black box that promised miracles but delivered, in early testing, constant malfunctions. The first B-29 seconds equipped with the system arrived at training bases in Kansas and Nebraska in mid-1943, and the reports from gunnery instructors were scathing. The system froze at altitude. The gyroscopes tumbled during evasive maneuvers. The hydraulic actuators responded too slowly, or too quickly, creating a lag between the gunner's tracking input and the turret's movement. Gunners complained that the system fought them, that it moved the guns away from where they were trying to aim, that it was impossible to develop any intuitive feel for how to use it effectively. Boeing's test pilots reported similar frustrations. The central fire control added weight and complexity to an aircraft that was already pushing the boundaries of what was mechanically feasible. The B-29 was the most expensive weapons development program of the Second World War, exceeding even the Manhattan Project in total cost. Every pound of additional weight reduced range, bomb load, or both. Every additional system increased the likelihood of mechanical failure. And for what? A computing gunsight that, in controlled testing, seemed to miss as often as it hit. By late 1943, there were serious discussions within the Army Air Forces about removing the central fire control system entirely from production B-29 seconds and reverting to manual sights. The war was not waiting for perfect technology. The B-29 was desperately needed in the Pacific, where the advance toward Japan required airfields in the Marianas and a strategic bombing campaign that could strike the Japanese home islands. If the computing sites were delaying deployment or reducing reliability, they were a liability, not an asset. But a small group of engineers and forward-thinking officers argued for patience. The system, they insisted, was not fundamentally flawed. It simply required refinement, better training protocols, and most critically, actual combat data to validate its performance under realistic conditions. General Curtis LeMay, who would later command the 21st Bomber Command and oversee the strategic bombing of Japan, was among those who advocated for keeping the system. LeMay had a reputation for ruthless pragmatism. He cared nothing for elegant engineering or theoretical performance. He cared about results. And the mathematics, he believed, were undeniable. If the system worked as designed, it would revolutionize bomber defense. The breakthrough came not from further engineering refinement, but from a shift in training philosophy. Instead of teaching gunners to use the computing sight like an enhanced manual sight, instructors began teaching them to trust it completely. The key insight was counterintuitive. The gunner's job was not to aim, but to track. Keep the target centered in the reticle. Let the computer calculate deflection. Don't try to lead the target manually. Don't try to anticipate its movement. Just track smoothly and let the machine do what it was designed to do. This required a psychological adjustment that many gunners found nearly impossible. It meant surrendering control, abandoning years of training and instinct, and placing absolute faith in a mechanism they didn't understand. But the gunners who made that adjustment, who learned to relax their grip and follow the target with smooth, steady movements, discovered something remarkable. The system worked. In live-fire exercises over the Gulf of Mexico in early 1944, B-29 gunners using the central fire control system achieved hit rates 5 to 7 times higher than gunners using manual sights. 3,000 rounds per kill dropped to 500, then to 300. By the time the first B-29 combat missions launched from bases in China in June of 1944, the system had been debugged, the training protocols refined, and the gunners grudgingly, skeptically, had learned to work with the technology rather than against it. But the real test would come not over China, where Japanese fighter opposition was sporadic and often poorly coordinated, but over Japan itself, where the empire's most experienced pilots would encounter American bombers equipped with a technology they had no reason to expect and no tactical doctrine to counter. The Japanese fighter pilot corps of late 1944 was not the elite force that had swept through the Pacific in 1941 and 42. Most of the veteran pilots who had trained for years before the war were dead, shot down over the Solomons, New Guinea, or the Philippines. Their replacements were younger, less experienced, rushed through abbreviated training programs as Japan's industrial capacity strained to replace both aircraft and pilots at a sustainable rate. But they still flew the Zero. And the Zero, despite its limitations, remained a formidable interceptor in the hands of even a moderately skilled pilot. It was faster than the B-29 inches level flight, more maneuverable, and armed with cannons that could shred a bomber's aluminum skin. Japanese tactical doctrine for intercepting B-29 seconds was based on lessons learned from fighting B-17 seconds and B-24 seconds over the Pacific and Southeast Asia. Attack from below and behind, where the bomber's defensive fire was weakest. Coordinate attacks from multiple angles to overwhelm the gunners. Close quickly, fire a short burst, then break away before the defensive fire could concentrate. It was a doctrine that had worked, with varying degrees of success, for 3 years. There was no reason to believe it would fail against the B-29, but the B-29 was not a B-17. It was larger, faster, pressurized, and capable of operating at altitudes the Zero could barely reach, and critically, it was defended by a system that made traditional fighter tactics not just ineffective, but suicidal. The first mass raids against Japan launched from the Marianas in November of 1944, and the Japanese response was immediate and aggressive. Dozens of fighters rose to meet each formation, vectored in by ground radar and early warning networks that gave them precious minutes to gain altitude and position. The pilots expected the usual chaos of bomber defense, scattered fire, individual gunners tracking individual threats, opportunities to exploit gaps in coverage during the crucial seconds when one gunner lost sight and another acquired the target. Instead, they encountered something that seemed to defy the logic of aerial combat. The B-29 seconds flew in tight formation, their turrets moving with synchronized precision, tracking fighters before they entered effective range. The defensive fire didn't spray wildly across the sky. It converged, streams of 50 caliber tracers intersecting at precise points in space, creating kill zones that fighters couldn't evade because the zones moved with them, anticipated their maneuvers, adjusted for their speed and angle of approach. Lieutenant Yamaguchi's experience was not unique. Post-war analysis of Japanese fighter pilot reports from late 1944 through early 1945 reveals a consistent pattern of confusion, frustration, and mounting casualties. Pilots described B-29 defensive fire as uncannily accurate, impossible to evade, and in several cases, as if the gunners could see the future. The language is telling. These were not men encountering superior training or better reflexes. They were encountering a category of technology they had no framework to understand. The statistics tell the story with brutal clarity. In the first 3 months of B-29 operations over Japan, from November 1944 through January 1945, Japanese fighters downed fewer than 2% of attacking bombers. This was not due to lack of effort or courage. Japanese pilots flew into walls of defensive fire, pressed attacks to point-blank range, rammed bombers when their ammunition ran out. But the mathematics had shifted. The central fire control system had changed the calculus of bomber defense so fundamentally that traditional fighter tactics were no longer viable, and the cost to Japanese fighter forces was catastrophic. Conservative estimates suggest that in the same 3-month period, B-29 gunners claimed more than 600 aerial victories. Not all of these claims were valid. Aerial combat statistics are notoriously inflated, with multiple gunners often claiming credit for the same kill. But even if the actual number was half the claimed total, it represents a staggering loss rate for an air force already stretched to the breaking point. By December of 1944, Japanese air defense commanders faced a problem that had no obvious solution. The conventional wisdom of fighter tactics, speed, maneuverability, and aggressive close-range attacks had become a death sentence against B-29 formations. Pilots who survived their first encounter with the Superfortresses returned with reports that sounded less like combat debriefs and more like descriptions of fighting a supernatural opponent. Captain Yasuhiko Kuroe, a veteran pilot with 11 confirmed kills over China and the Philippines, filed a report after engaging B-29 seconds over Tokyo on November 24th that captured the psychological disorientation these encounters produced. The American gunners do not aim, they simply follow. I have seen tracer fire curve to meet fighters in a turn, adjusting for deflection as if guided by an invisible hand. When I attacked from a 45-degree angle below, diving at maximum speed, the ventral turret rotated to the precise angle of interception before I entered effective range. The stream of fire did not search for me. It was simply there, waiting for me to fly into it. Find this story engaging? Please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. What Kuroe and his fellow pilots were experiencing was the practical expression of a technological principle that had seemed almost trivial when General Electric's engineers first proposed it. Remove human error from the deflection equation, and accuracy increases by an order of magnitude. The Mark 15 computing site didn't make American gunners better shots. It made the concept of aiming obsolete. The gunner's skill was no longer measured by his ability to calculate lead angles or estimate closure rates. It was measured by his ability to track smoothly and trigger discipline, to hold fire, until the computer confirmed a solution, then release a short, precise burst rather than a long, wasteful spray. The system operated through a series of mechanical calculations that would have been impossible for a human to perform in real time. When a gunner acquired a target and began tracking it in his sight, a set of gyroscopes within the computing mechanism measured the angular velocity of his tracking movement. This data fed into an analog computer that calculated the rate of change in 3 dimensions, compared it to known ballistic data for the .50 caliber Browning machine gun, and computed the required deflection angle. Servo motors then adjusted the gun position independently of the sight position, offsetting the barrels by the precise amount needed to place bullets in the target's future position. The entire process took fractions of a second. The gunner saw only a reticle and a target. He had no direct awareness of the complex mechanical ballet occurring behind his sight picture, the whirring gyroscopes, the flowing hydraulic fluid, the spinning gears translating angular momentum into predictive geometry. He simply kept the target centered, and the system did the rest. But the technology was only half the equation. The other half was coordination. Unlike earlier American bombers, where each gunner operated independently, the B-29 Central Fire Control System allowed a single gunner to control multiple turret positions simultaneously. The Central Fire Control Officer, typically positioned in the upper forward turret, could see the entire defensive sphere around the aircraft through a sophisticated sighting blister. When he tracked a target, he could activate any of the remote turrets, including the tail position, the lower forward turret, or the upper aft turret, directing their fire without the individual turret gunners needing to acquire the target independently. This meant that a fighter attacking from below and behind could find itself engaged not just by the tail gunner, but by the Central Fire Control Officer directing the upper aft turret, the lower rear turret, and potentially even the side-firing guns if the aircraft was equipped with them. The converging streams of fire that Japanese pilots described were not coincidental. They were the deliberate product of a system designed to create overlapping fields of fire that a single controller could coordinate with the precision of a conductor directing an orchestra. The psychological impact on Japanese pilots cannot be overstated. Fighter combat in the Second World War was, at its core, a contest of skill, nerve, and split-second decision-making. Pilots trained for years to develop the instincts necessary to survive, reading an opponent's maneuvers, anticipating their next move, exploiting their mistakes. Against the B-29, these skills became irrelevant. The bomber didn't make mistakes. It didn't panic. It simply calculated, adjusted, and fired. Pilots found themselves fighting not against other men, but against a mechanical intelligence that never tired, never flinched, and never missed by more than the inherent dispersion of the guns themselves. By January of 1945, Japanese tactical commanders began implementing desperate countermeasures. Some units attempted night attacks, reasoning that the computing sites would be less effective without visual tracking. This proved partially successful. The system's effectiveness did decline in darkness, but it also reduced the fighter's accuracy proportionally, and the B-29's radar-directed tailgun remained operational even in complete darkness. Other units experimented with head-on attacks, diving from high altitude directly into the bomber formations, hoping to minimize the time spent in the defensive fire zone. This tactic produced occasional successes, but resulted in catastrophic casualty rates, with pilots either shot down during the approach or unable to pull out of their dives in time. The most sophisticated response came from units equipped with heavy cannon-armed interceptors, including modified versions of the Ki-45 and the experimental J-2M Raiden. These aircraft were designed to engage bombers from beyond the effective range of OPSA, defensive .50 caliber fire, using 37mm or even larger cannons to inflict damage from distances of 800 to 1,000 meters. In theory, this allowed the interceptor to remain outside the B-29's defensive envelope. In practice, the Central Fire Control System's effective range was considerably greater than Japanese intelligence estimated, and the long-range cannon attacks required a level of precision that few pilots could achieve against a moving target at high altitude. There were, of course, successes. Japanese fighters did down B-29 seconds, particularly during the early months of the campaign, when American crews were still learning the most effective defensive formations and when mechanical failures occasionally disabled the fire control systems. On January 9, 1945, a formation of superfortresses attacking aircraft factories near Nagoya lost 6 aircraft to a coordinated fighter assault that overwhelmed their defenses through sheer numbers, more than 70 Japanese fighters engaging 30 B-29 seconds simultaneously. But these victories were exceptions, achieved at enormous cost. Post-mission reports estimated that the Japanese lost more than 20 fighters in that engagement, a kill ratio that no air force could sustain. The individual accounts from American gunners provide the other side of this story, and they reveal an interesting psychological transformation. The same gunners who had mocked the central fire control system during training became its most fervent advocates after their first combat mission. Staff Sergeant Michael Barron, a central fire control officer on a B-29 named City of Los Angeles, described his first encounter with Japanese fighters in a letter home, dated December 3, 1944. "We were about 20 minutes from the target when they hit us. I counted at least 8 zeros, making simultaneous attacks from different quadrants. 6 months ago, that would have been a death sentence. We'd have been lucky to get half of them. But I activated the upper aft and lower rear positions, tracked the nearest fighter through my sight, and watched the tracers converge exactly where the computer said they would. The zero flew right into the stream. Didn't even try to evade. I don't think he realized he was in my sights until the rounds started hitting. The whole engagement lasted maybe 15 seconds. We claimed 4 confirmed kills and 2 probables. We didn't lose a single aircraft from our squadron." This confidence, this almost casual description of a life-or-death combat engagement, reflects a fundamental shift in the psychology of bomber defense. American gunners began to trust the system, not because they understood how it worked. Most couldn't have explained the mechanical principles behind the computing sight, but because it worked. The proof was empirical and undeniable. They survived missions that should have killed them, and the fighters that should have shot them down fell burning from the sky instead. The technical challenges of maintaining the central fire control system in combat conditions were considerable. The hydraulic lines required constant monitoring for leaks. The electrical connections were vulnerable to combat damage. The gyroscopes needed periodic calibration, and the analog computers occasionally produced erroneous solutions if they were jarred too violently during evasive maneuvers. Crew chiefs and armament specialists spent hours between missions, checking, adjusting, and repairing the system, knowing that a malfunction could mean the difference between survival and a fiery death over enemy territory. But despite these challenges, the system's reliability improved dramatically over the course of the campaign. Modifications implemented in early 1945 addressed many of the initial problems: better sealing for hydraulic connections, redundant electrical pathways, shock-mounted gyroscopes that could withstand more violent maneuvers. By March of 1945, when General LeMay shifted tactics from high-altitude precision bombing to low-altitude incendiary attacks, the central fire control system had achieved a reliability rate above 90%, an extraordinary figure for complex military technology operating in the harsh environment of high-altitude combat. The low-altitude missions presented a different set of challenges. At altitudes between 5,000 and 8,000 feet, Japanese fighters could operate at peak performance, and the B-29 seconds lost the protection of extreme altitude that had limited enemy interception options. But the fire control system proved equally effective at low altitude, and in some ways more so. The denser air improved turret response times, and the reduced range to targets meant higher hit probabilities, even with the system's inherent dispersion. The night of March 9th to 10th, 1945, the Great Tokyo Firebombing raid saw more than 300 B-29 seconds attack the Japanese capital at low altitude in darkness. Japanese fighters rose to meet them, guided by searchlights and the glow of the fires below. It was exactly the kind of confused, chaotic night battle where traditional defensive tactics should have broken down, where individual gunners should have been overwhelmed by targets coming from multiple directions in poor visibility. Instead, the central fire control system's radar-directed capabilities and the coordination between turret positions allowed the bombers to maintain effective defensive fire even when visual identification was nearly impossible. Of the 325 bombers that attacked Tokyo that night, 14 were lost, a casualty rate of just over 4%. Japanese fighter losses numbered in excess of 40 aircraft. These numbers require context to understand their significance. In the Great Daylight Raids over Germany, before the introduction of long-range fighter escorts, American bomber groups sometimes suffered casualty rates exceeding 25%. Entire squadrons could be effectively destroyed in a single mission. The attrition was so severe that the strategic bombing campaign nearly collapsed under the weight of unsustainable losses. The B-29 raids over Japan, by contrast, maintained casualty rates that rarely exceeded 5%, even during periods of intense Japanese opposition. The difference wasn't superior armor, higher speed, or better pilot training. It was the central fire control system, turning American gunners into precision marksmen who could engage enemy fighters with an effectiveness that defied every previous standard of bomber defense. By spring of 1945, Japanese fighter opposition to B-29 raids had declined sharply. This wasn't primarily due to lack of will or deteriorating pilot skill, though both were factors, but to simple arithmetic. The Japanese air defense system was bleeding, fighters faster than the industrial base could replace them. Every raid resulted in a net loss, bombers downed versus fighters destroyed. And the ratio was consistently, devastatingly unfavorable to Japan. For every B-29 shot down, Japanese fighters were falling at rates of 5, 10, sometimes 15 to 1. The final months of the war saw Japanese air defense shift toward kamikaze tactics, not the organized kamikaze units of the naval war, but individual pilots making desperate ramming attacks when their ammunition ran out or when they judged that conventional attacks were futile. These tactics occasionally succeeded, but at a cost that was, in the truest sense, unsustainable. An air force that trades pilots for bombers on a one-to-one basis is engaged in a war of attrition it cannot win. An air force trading 10 pilots for one bomber is engaged in a form of strategic suicide. The post-war analysis of B-29 operations over Japan credits the central fire control system with saving thousands of American lives and contributing materially to the success of the strategic bombing campaign. Conservative estimates suggest that without the computing sites, B-29 casualty rates would have been 3 to 4 times higher, potentially forcing a premature end to the bombing campaign or requiring a massive increase in production and crew training that the United States may not have been able to sustain. But perhaps the most profound impact of the technology was psychological rather than tactical. The central fire control system represented a category of warfare that the Japanese military, and indeed, most military establishments of the era, were unprepared to counter. It was not a weapon that could be matched through superior training, greater courage, or tactical innovation. It was a fundamental technological advantage that could only be countered with equivalent technology, and Japan lacked the industrial capacity, the engineering expertise, and most critically, the time to develop such systems. Japanese engineers were aware of lead computing sites. German researchers had experimented with similar technologies, and there is evidence that Japanese military attaches in Germany received technical briefings on these developments. But knowing that a technology exists and possessing the industrial infrastructure to mass produce it are entirely different challenges. The central fire control system required precision manufacturing capabilities, advanced hydraulics, sophisticated analog computing components, and quality control standards that Japanese industry of 1944 and 45 could not meet, even had there been unlimited time and resources to attempt development. This reality that technological superiority could create insurmountable tactical advantages foreshadowed the nature of warfare in the second half of the 20th century. The B-29's computing sites were an early expression of a principle that would dominate military thinking for decades. Information processing speed and accuracy could matter more than traditional measures of military power like firepower, armor, or maneuverability. The fighter pilot's skill became secondary to the bomber's computational capacity. The equation changed, and one side adapted while the other could not. The men who had initially mocked the system as ridiculous, who had insisted that instinct and experience were superior to mechanical calculation, had been forced by reality to revise their assumptions. They learned, as countless soldiers have learned throughout history, that survival often depends on the willingness to abandon comfortable certainties and trust in new methods, even when those methods seem counterintuitive or unreliable. The 600 victories claimed by B-29 gunners, even if the actual number was lower, represent not just destroyed aircraft, but the systematic dismantling of Japan's air defense capability during the final year of the day war. Each fighter lost was a pilot who could not be easily replaced, an aircraft that represented hundreds of hours of manufacturing capacity, a small but measurable degradation of Japan's ability to contest American air superiority. The cumulative effect was the creation of a strategic environment in which American bombers could operate with near impunity, devastating Japanese cities and industrial capacity, severing supply lines, and laying the groundwork for the final phase of the Pacific War. In the decades following the war, the Central Fire Control System became a footnote in the larger narrative of strategic bombing, overshadowed by more dramatic technologies like radar, the atomic bomb, and jet propulsion. But for the men who flew in B-29 seconds over Japan, and for the Japanese pilots who tried and largely failed to stop them, the computing site represented something more fundamental than a mere technological innovation. It represented the collision between industrial-age assumptions about warfare and the emerging reality of a world in which mathematics, applied with precision and speed, could determine outcomes more decisively than courage or skill. Lieutenant Sadao Yamaguchi survived the war. He flew more than 30 missions against B-29 formations and claimed 3 confirmed victories, though his own aircraft was damaged on at least 7 occasions. In interviews conducted in the 1980s, he was asked what he remembered most vividly about fighting the Superfortresses. His answer was telling, "The feeling that we were not fighting men, but fighting the future. We had our courage and our training, and they were not enough. They had their machines, and their machines made them invincible. I realized, during those missions, that Japan had already lost the war. We just didn't know it yet." That realization that technological disparity could render bravery irrelevant was perhaps the most profound lesson of the B-29's defensive systems. The war had been decided not just by industrial capacity or strategic resources, but by the ability to translate theoretical advantages into practical battlefield systems faster than the enemy could adapt. The Central Fire Control System was one expression of that principle among many, but it was an unusually pure one, a direct technological answer to a tactical problem, implemented with such effectiveness that it fundamentally altered the mathematics of aerial combat. The legacy of this technology extended far beyond the Second World War. The principles of lead computing, automated fire control, and centralized coordination of defensive systems became foundational concepts in military aviation. Modern fighter aircraft use descendants of the same basic technology, translated into digital form and integrated with radar and missile guidance systems. The idea that a computer could aim better than a human, once considered ridiculous and impractical, became accepted doctrine. And somewhere in that, transformation, the B-29 gunners who had learned to trust their machines over their instincts proved a point that transcended their immediate tactical situation. That the future of warfare belonged to those who could harness computational power most effectively, not necessarily to those who possessed the most traditional forms of military skill or martial virtue. The sky above Japan in 1945 was a proving ground for this principle. Japanese pilots, flying with desperate courage against impossible odds, learned the bitter lesson that Lieutenant Yamaguchi articulated so clearly. Machines, properly designed and deployed, could make men invincible, or at least invincible enough to win a war. The 600 Zeros claimed by B-29 gunners were not just aircraft. They were proof of a new reality, written in fire and tracer rounds across the skies of a dying empire. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.